So in today's class, we are going to see some CMOS testing methodologies. Okay. So if you see testing is one of the most expensive parts of the chips. Okay. Why I say that is if you make an chip and then you ship that, okay, without confirming whether it's working 100% meeting to the design requirements, then it can sink the company also, right? So the cost involved in recalling them a defective product is enormous. Okay. And so you need to have some testing also before you actually ship the consignment. There has to be some method where I can do a foolproof testing to see to it that the components are meeting the required specifications. Okay. Now for that, okay, there has to be an test setup. Okay. And also within the chip there has to be some a provision for testing the design. Okay. The design itself has to incorporate, okay, the provisions for testing, right? So if you see, the logic verification accounts for 50% of the design effort. Many a times it is pretty easy to design something, but to verify whether that design post fabrication, if it's working fine, you need to include as many as 50% of your design effort will go towards designing the components that will facilitate testing post fabrication. Okay. As an example, if you see, okay, Intel had that floating division bug. Okay. This logic error in the chip was not detected earlier. It was detected only after around 1 million chips were shipped, and then the recall cost was around $450 million. Okay, so it is so, and hence you can understand, see how important testing is. Okay, so in today's class we are going to see the various concepts and processes of testing. So the first, even before the fabrication, okay, we do some pre-fabrication test or logic verification. Okay. So this is done at the simulation level just to ascertain that the post fabrication the chip would work fine in various environmental conditions. Okay. Now we generally do the corner method. Okay, what is the corner method? That is shown in this cube out here. Where you have slow or medium fast devices. Okay. So when you do most of the EDAs will provide the models for the N MOSFETs and P MOSFETs. Okay. There you have these models. Slow means an slow NMOS and a slow PMOS. Medium indicates a medium NMOS and a medium PMOS performance wise. Okay. And fast means a fast NMOS and a fast PMOS. Okay. So these are the three different types of NMOS and PMOS which will be available in the EDA tool. Okay. And these models they come from the fab lab, right? So based on the statistics they get after fabrication of a large number of chips over a period of time, they refine these models, right? So when they say 1 million chips have been fabricated and they have tested several of them, and a few they found to be slow, and they have the statistical data, right? Some devices they operate at medium speed and some at faster. So based on that statistical data, the fab lab gives a slow, medium and fast models for the NMOS and PMOS. So whenever we do when we design a circuit, we have to ensure that the circuit works for all these three corners, also for various temperatures like 0 degree, 85 and 125 degrees Celsius, and this is for a 28 nanometer where the nominal voltage is just an example. If the nominal voltage is 9 volt, So 10% above, that is 0.99 volt, and 0.18 below the nominal voltage. So if you see, there are 3 axes out here. So there will be 29 different sets of simulation conditions. Okay, and like for example, 0 degree, 0.81, and slow. 0 degree, 0.9 nominal voltage and slow. 0 degree, 0.99 and slow. Similarly, so you have a 3 into 3 into 3, total 29 different conditions. Okay, so this is known as corner analysis. Okay, this is a very useful tool. So unless you are there will be definitely the total performance of the circuit in all these corners will not remain the same. So they are going to be some variations. But even in the worst case scenario, we have to see to it that the minimum required specifications are met. Okay, so this kind of testing is done prior to the fabrication, right? And these are known as logic verification, right? And this is again another example of a 45 nanometer process, slow, medium, fast, and this is a -40, 25, and 125, and 1.1 is the nominal voltage here. So 1.21 and 0.99. So these are the voltage ranges, 10% of the VDD, right? So these obviously in each and every design technology file which is provided by the fab lab, so there will be model files. Okay, so those model files you can select one of these 3 for each simulation run. You can change from SS to MM to FF, and also the EDA tools provides for temperature settings, and these are the voltage sources which we use. Okay, at the schematic level itself. So this can be this will be available in the simulation environment. This will be available in the model file, and this is in your schematic on these values. So these can be set. So all this 27 simulation in this, all this 27 corners need to be done before the chip is sent for fabrication. Okay. Corner analysis simulates your design with minimum and max value for each of the parameter, but does not reproduce the mismatching between devices. Like for example, a corner device, it won't say how a slow NMOS would work with a fast PMOS. Okay, so that kind of an analysis is not possible. Okay, corner analysis. So some of the EDA tools, they also provide where in the model files, you can vary the thickness, resistor value, and capacitor value for worst speed, worst power, okay, worst 1, worst 0. Okay, so these kind of settings are also possible. Okay, so if you want to do a more detailed analysis, then even the EDA tool out here, they provide these kind of settings also. If you see here, it is set for like the cap, the capacitor model files. The capacitor is been set for worst power. Similarly, the MOS is set for worst speed. So those kind of settings also can be done. Okay, so that will give you. But generally speaking, this is good enough. Why I am telling this is good enough is, let me show you this out here. So if you see here, when the chip gets fabricated, okay, this area, okay, the chip might get all the NMOS and PMOS available in this particular area, right? And they might be working as fast. Okay, and unless you have all your NMOS out here and the PMOS out here, then you could have an issue with this area. And in this area, they could be during the fabrication process, all the chips could have been fabricated in a slow. Some defect might have occurred wherein these devices are operating in a slow fashion, and these are operating at a fast fashion. Okay, so you will have mismatches if you have put all your NMOS here and all your PMOS devices here. So obviously the corner analysis will not capture such defects, because here we take slow and medium and fast. Okay, so why this is taken is, if you see here, this is the entire wafer. Okay, so this small is the one particular chip. Okay, so generally what happens, this full chip will be an either it will be a slow or a fast or medium, and this entire chip, okay, it is not fabricated right, a single chip. The entire, on a wafer there will be hundreds of chips, right? So in the wafer itself, okay, some portion of the wafer you might have good devices being fabricated, and on some portion of the wafer it will be slightly slower devices might get fabricated, okay, because of the fabrication issues. So if you see the NMOS and PMOS, generally they could land up being slow, fast, or right, and medium, right? So the very rarely on these in the border lines you will find, okay, the mix of fast and slow devices. So that is the reason I said this is good enough. So traditionally this is the model which was being used for many years, and still a lot of people do use this. Now, although the modern EDA tools gives more flexibility, okay, in terms of setting worst power and worst speed, and worst 1 and worst 0, okay, this gives you an tool for in-depth analysis, but traditionally this was the thing which was being done. Okay, so this is about okay, and then you also have something known as Monte Carlo analysis. Okay, this is also these days done. Okay, for every circuit you do Monte Carlo analysis also. What it does is, it randomly picks for your simulation, it randomly picks up NMOS from the entire region, okay, and PMOS from the entire region. Not only NMOS, PMOS, other devices like capacitors, resistances and all. Okay, so varying parameters, it doesn't mix and match of varying not only slow, fast, but a mix and match of all the parameters. So you need to, only drawback is you need to do a large number of simulations so that the results are acceptable results. Okay, if you just run Monte Carlo analysis for very few samples, then the results will not be that dependable, right? So if you have to have reliable results, then you need to do Monte Carlo analysis with a sample size of at least 250 or more. Okay, so that kind of analysis also. So your EDA tools like Cadence, they provide this provision to do Monte Carlo analysis. So once you design your circuit, so you can do this corner analysis. After having done the corner analysis, if it is meeting the minimum specs in all the 27 corners, then you can also run a Monte Carlo analysis in which the simulator, the EDA tool would pick up different properties of NMOS and PMOS, and it will keep varying the properties of NMOS and PMOS, catering for the various fabrication issues, and it will give you results. Okay, and then you can see that after the Monte Carlo analysis, if on most of the runs, if it is meeting the desired specifications, then you can go ahead with your fabrication. Okay, so that is about prefabrication testing. Okay, now also this is, as far as this is concerned, this is being done for the your circuit which you have designed, but also on the chip you need to have a design incorporated which allows you observability and controllability. Okay, that is known as design for testability. Okay, what is observability? That is, in a post fabrication you should be able to observe each node, what is happening, okay, through an external pin of the chip, right? So there could be several blocks in your chip. So if you are able to see as many intermediate points as possible through an external chip, then you will be able to diagnose whether the chip is working properly. You will be able to verify if the chip is working properly, and if you are not getting the desired results, you can see what is wrong. So for that you need to have observability, right? That means from each stage, if you could get an output somehow to one of the pins, then you can observe stage by stage whether the output is available or not, right? Controllability is like if you have several stages, but while testing you should be able to give some test vectors into each of those blocks, right, by either giving an input 0 or 1, right? So that also for during testing, so there should be some pins through which you should be able to force a node to 0 or 1. Okay, so that is known as controllability. So generally you should have both for controllability and observability in your design. Okay, only then you will be able to do a good testing post fabrication, right? So the combinational logics, for combinational logics it is very easy to observe and control, whereas for finite state machines it is difficult, right? So you might have to do an exhaustive testing, because even the previous state requires to be captured, right? So the testing becomes even more difficult in that particular case. Nevertheless, it should be done, and it can be done. Right, now let's see what are the kind of faults which come in these VLSI circuits post fabrication. Okay, so how does a chip fail? Okay, generally once suppose this logic has been implemented, so the faults, there are simple faults which they come, which is known as stuck at faults. Okay, for example, you can say the input C out here, this input line to this AND gate is stuck at 0. That means even if this C is coming from some other block, irrespective of whether a 0 or 1, which is coming from the previous blocks, the input to this particular AND gate is stuck at 0. It is continuously 0 out here, right? So these are known as stuck at faults. Okay, so it could get stuck at 0, or it could get stuck at 1, because during fabrication such faults can happen. Okay, because there will be some wire, okay, which is interconnecting this particular gate of this MOSFET with coming from some other. So while the wire is being routed, there is a possibility that it can get shorted to the ground because of the fabrication issues, and that is how this results in a stuck at 0. Similarly, the wire which is getting some signal to one of the gates or nodes, and if it gets shorted to VDD during fabrication, okay, because that's what is known as the errors in the fabrication. Okay, then it can get stuck at 1 also if it gets, if these wires they get somehow, okay, shorted to the VDD line. Okay, so you could have an stuck at 0 fault, or you could have an stuck at 1 fault. Okay, so that is possible. So in these cases, if suppose this is stuck at 0, if I have to find okay, so whether this is stuck at 0 or not, so the kind of test vector which is to be given out here will be 0 0 1 1. If I give 0 0 1 1 and still I am getting a 0 out here, that means this node, okay, either this node or this node is stuck at 0, right? So that is how you can different test patterns are there. So for each of these nodes, to find out if there is a stuck at fault, you have to give a test pattern. So for this particular fault, if you have to verify whether this is stuck at 0, the test pattern which needs to be given will be 0 0 1 1. Is it okay? Is it understood? Yeah, Bara, is it okay? Okay. Okay, so there could be here we are talking about in a small logic circuit, one stuck at 0. Okay, there could be circuits in which there could be more than one okay, that is in the next slide. Okay, here we are talking about okay, this node is stuck at 0. Now here we talked in the previous example. Okay, let me go here. Yeah, multiple stuck. No, okay, now there could be a situation where this is stuck at 0 and this is stuck at 1. Okay, so in these cases it is very difficult to actually pinpoint what is what has gone wrong, right? So you might land up doing requiring more than many test vectors to actually identify these kind of faults. And generally for small circuits we don't consider multiple stuck at faults. Okay, so we have to have that much belief in our technology that one odd mistake can happen. The probability of having many faults within a small confined chip area will not be there. Okay, because otherwise if you have to cater for multiple stuck at faults, then your design for testability becomes very complex in nature. Okay, so we are going to the entire testing philosophy is based on a simple assumption that there won't be multiple faults within a small area. So faults are not regular, but it's an exemption, right? The technology has to cater for no fault in a fabrication, but one not small fault can happen. So that is the assumption. So because if you try to assume that during fabrication there can be n number of faults, okay, then your testing is going to become even more complex than the main circuit itself. Okay, so we can't afford to do that. Okay, so that is known as multiple stuck at line faults. Okay, so here if you see here what is the kind of test patterns which are required for various faults. If you see here, here if I have to identify if this particular node X, if it is stuck at 0 or not, what do I do? Okay, so I can give this test vector, right, 0 0, right, and then 1 1. So I have to get an output as 1. If I am not getting 1, that means the node X, because I am giving 1 1 at C and D, so output node X has to be 1, right? So that means if I give 0 0 1 1, so I can verify if it is stuck at 0 or if it is stuck at 0. Similarly, if it is if you have to verify if this Y is stuck at 0, then I can give 1 1 here and 0 0 here and verify the results at the output. So these are the different test patterns which are available. Okay, so you don't have to actually give 4 inputs, 2 to the power of 16 test inputs, right? So so if you have a circuit like this, okay, we can just give these two this one test vector to verify this particular path. Okay, if there is a stuck and 0. Similarly, I can give 1 1 and 0 0 to verify if there is a stuck at fault at 0 here. So testing is all about not giving a full all the type of input variation variable combinations which is possible, but it is about trying to minimize the test conditions judiciously by evaluating the circuit and accordingly designing the minimum number of test vectors which is required. Okay, because this we are just talking about one particular gate. So when you look at it at an VLSI circuit, there will be hundreds and thousands of gates, right? So if you do an exhaustive checking by giving all possible type of inputs, okay, so you could have multiple stuck line faults also. Okay, that means you could have an stuck at 0 here, you could have an stuck at stuck at okay, stuck at 1 also out here. So in this case what happens is if you are going to have multiple faults like this, then you need to have a bigger, if you are going to consider multiple faults, then you will have to have a large number of test vectors to verify. Okay, so generally we assume that there is not going to be several stuck at faults, the technology needs to take care of that. Okay, so while we are designing for testability, we assume that there is going to be only one odd faults out here, because if you start catering for multiple faults in within a small circuit, your testing will become very complex. Okay, so you believe in your technology that now more or less generally everything will be fine. One or faults would appear, and then we need to have a circuit which can verify that. Okay, so that is known as multiple stuck at line faults, and then so one way of trying to do a testing is do exhaustive testing. That means if there are 4 inputs, you need to have 2 to the power of n, right, and that is 16 different input combinations, and check what is the result outside, right. But that that is a foolish way of doing it, because suppose in a chip, if you have the thousands of gates like this, if you are going to do an exhaustive checking, then it will be very time consuming, right. So you can't do that. So suppose this is a circuit out here. If I can just try check if this is stuck at 0 here. How do I do that? I can give 0 0 1 1 here, and if I get an 1 output, that means this X line is working fine, right. Similarly, if I have to find out if this is this is stuck at 0, if Y, so I can give 0 0 1 1 here, 0 0 here, and if I find that the output is 1 here, then I can say okay, this path is also correct. Okay, can anybody tell me what would be the test vector to verify, right, if there is a stuck at 1 fault here? Anybody, can you just make a guess? What should be the test vector? Okay, let me repeat the question. Yeah, so answer correct, 0 0. So if I give 0 0 0 0 here, and if I get a 1 here, I can assume that one of them is now here or here it is stuck at 1. So now if you see here, 2 to the power of 4 is 16, right? I don't require those many test vectors. If I just give 3 test vectors, 0 0 1 1 1 1 0 0 and 0 0 0 0, more or less I get the correct functioning of this particular circuit, right. So I can do that. So that is how. So you have to judiciously select the number of test vectors which is required to verify this design. Okay, so there is no point blindly going for all input combinations. So that is how, that is known as so the test engineer. Okay, so he has to depending on each circuit. Okay, so this is going to be specific for this circuit, so he has to have good knowledge about the circuit also. So the test engineer has to work in conjunction with the chap who has designed the circuit to understand how the circuit function, and then accordingly design the test circuit as well as the test vectors. Okay, have to be carefully selected. Otherwise, post fabrication we will keep spending lot of time trying to ascertain whether it is working fine or not. Okay, so here again, so another kind of faults. Now what is backtracking? Maybe like if you have an circuit out here, like if you are getting an you take a big model, give certain inputs, and you try to find out what is the output, and if you are not getting the desired output, then you can go one step behind. Okay, and then try to find out if it is a fault here or a fault here, because in certain fault tolerant circuits, you might have an, like if it is an 3 gates out here, there could be one. I am just giving a rough example. There could be one more gate here which is normally not connected here, but during testing, if you find there is an error out here, there you might be able to bypass that and get this into the circuit. So there will be some multiplexer. So some in some critical blocks. Okay, like the you have several adders in a multiplexer, in a multiplier, right? So if say one adder is at fault, then you should be able to replace, that is known as fault tolerant designs. You should be able to replace that one particular module. Okay, so generally we give test vectors and look at the output, and if it is not there, then you go one step behind and try to localize that fault, and then try to replace that particular gate. Okay, so when you design, if you have a fault tolerant design, you might have several, either you have this entire setup duplicate, right, or you could have like if one of these gates are duplicated, right. Okay, yeah, that's what I said. While testing, initially in the test, you might find if Z, there is a problem in the Z, it could be Y or X. So that is what you may do an backtracking. Okay, so you might have to go first. So instead of going ahead, trying to find out whether this thing is okay at each level. Okay, you can first test at do a testing at Z, and then keep moving forward. If there is a problem, you come back. Okay, okay, so that is, yeah, 0 0 0 0 is stuck at one test. Okay, so now the other kind of problems which come during fabrication is, this is known as a bridging. Okay, these two inputs getting shorted. Okay, so they could result in a wired or a wired AND connections. Okay, so like if you see here, if they are shorted. Okay, in this particular case, so they will become an wired AND, right. So so these kind of problems also, so they are known as bridging. Okay, so these kind of shortings also can happen. Now while these kind of shortings, you have to be very careful. What would be the final output? Suppose A is being driven by a VDD and B is being driven by by the ground. So there is a possibility that heavy current can flow in these wires. Okay, but these short circuits okay, are generally very thin in nature, and they will be of very high resistance. Okay, somebody wants to speak. I am picking up some noise. Okay, so if it is a 1 here, it is a 0 here. Okay, so there is a short out here. So so there is a possibility that okay, whatever is available at A is going as an input to both these devices. Okay, so they are known as a bridging fault. So these kind of things are also there. So accordingly, the test patterns have to be, so they could result in an wired AND and wired NOR kind of defects. So you have to be so your test pattern needs to cater for such faults also. Okay, now there could be, we were talking about stuck at 0 and stuck at 1 faults. There could be something known as stuck open faults also. Okay, what is it? Like if you see here, this particular circuit it's an AND gate where this is supposed to be interconnected, right? But because of fabrication, there is an open circuit out here. Okay, now because of this open circuit here, okay, if it is fault free, it will be right, a NOR gate. Suppose this is a NOR gate, so it will work like an NOR gate. But when it is if there is an open circuit out here, right, so this will work, this function, and this faulty this is the function which gets implemented, A plus B bar and A B bar and this is this is not a Z bar, but this is the previous value of the Z. Suppose Z is 1 earlier. Okay, before this. Now the after how will this become 1 when both A B are 0 0? So this is 1, and now A goes to 1. Okay, in that case this is supposed to come to 0, but it won't come to 0, right? So A B bar, so it will because there is no path for this to get discharged. So you will find here A is switched off out here. okay, but this node if it has to get discharged, okay, the path available is through A, but that is not available in this particular case. So you will find the function gets modified like this, okay. So it depends on the previous value of Z now out here, right. So now what are the kind of test vectors which are required, right. So these are stuck open fault requires 2 patterns. In this particular case 2 test vectors are required. First is 1 1. So you have to see it is getting pulled to 0, okay. The pull to 0 means first, and then you in the second case, and then you put A equal to 1, B equal to 0, and if it is retains this particular state, that means it's a floating node. So in this kind of faults, and so only one particular test vector might not do. Just to identify this fault, there will be a requirement of 2 test vectors put in this order, okay. So this now you see how testing is becoming a bit complex in nature, okay. Okay, now coming to here we saw these are the kind of faults which are seen in combinational circuits. Now how to do sequential circuit testing, right. So what is a sequential circuit? You have a combinational logics, and then you have some registers which will store the previous stage, okay. There could be n number of flip flops here which will save the previous values, okay. So in this case, if you see here, testing has become it's pretty difficult. So if you have n and m, the total number of test vectors will be 2 to the power of m plus 1 patterns, and also the sequence is also important, right. So because this might behave differently when the sequence given out here is different. So that is why sequential circuit testing becomes even more difficult, okay. So there are several approaches. First, in the first approach, it is known as the pseudo combinational circuit. So we try, like if it is ABC here, okay, we try to give a 1 out here, right, and see whether this circuit works fine or not, and then we try to give a 0 out here and see whether this circuit works fine out here, right. So to give a 1 out here, what do? We give 1 1 out here and give the clock here, and we assume that 1 has to come here, and then we verify whether we are getting the desired result here. Similarly, we give 0, one of them we give 0 here, and we take and then once we give the clock out here, we assume that 0 is going to be available here, and then we give the necessary test vector here and see the output, okay. So these kind of circuits we do the testing in 2 parts. First, for each of these flip flops, we will give an input so that the flip flop is set to 1, and then we give some input so that the flip flop is set to 0, and then we do the accordingly we give the rest of the test vectors and see whether the circuit functions or not. So if you see here, this is known as an y plus, okay. Y plus means the previous value, right. So that comes out here, right. And so from the D flip flop you have the previous value coming here. So you have we do that and test, okay. So these are the 2 paths, like you give 1 1 out here, and we assume 1 will be available here, and then we give a test vector out here, right, and see whether this is going to work fine, and then we give 0 1 here, and then we assume a 0 will be available here now here, and then we try to do an testing of this circuit. So we split this in testing into 2 parts, okay. First we give a kind of test vectors which will set this to 1, and then which will in the next set of tests where we are going to set this to 0 and do the testing, okay. So that is how we do testing where flip flops are involved in a circuit, okay. So now we have a certain designs for testability, right. So so there are 2 kinds of designs which is generally adopted. One is known as Ad-hoc design for testability, and the other one is known as scan path design. Okay. Rather than discussing the pros and cons of these designs, I'll cover these in the next few slides, so that you will this is the summary which you could have a look at this PDF later on. I'll discuss these issues, and during these while discussing these circuits, I'll cover these points in the next few slides. Okay. Ad-hoc design means, okay, now there are two blocks out here, right? So in these blocks, if you see here, there is no observability or nor controllability, right? So now if I have to observe here, I can take the output from here, right? So this becomes this point becomes observable, right? And also I have put this one indicates an OR gate. Okay. So here there is, I have put an OR gate out here, and this is known as the control, right? Here block 1 you can control, right? Block 2 you can observe, right? In the first, if you don't do anything out here, if this is what is there in the chip, okay, so you will have an input out here, so you can control block 1 and you can now observe block 2. Okay, so block 2 is not controllable here, and block 1 is not observable here. And what we have done here is we have taken out a pin out here. Now if you see input to the block, so it is controllable, and output is also, this also we are going to get into the one of the pins of the chips, so you can observe block 1 also. Now for block 2, okay, I have an OR gate here. Okay, so when I give the control pin as 0, it will do a normal functioning, right? So during normal operation, I give a 0 out here. So block 1, this is an OR gate, so it gets so block 1 gets connected to block 2. Okay. Now if I give the control signal as 1 here, okay, then I am forcing a 1 into the block 2. So I can see the output and verify whether this block 2 is working fine if I am giving an input of 1. Okay. I can't check whether this block 2 is working fine if for an input 0, but just putting a single OR gate, I am able to just check whether this block 2 is going to work fine for an input of 1 out here. Okay. Similarly, instead of putting an OR gate, if I put an AND gate out here, right? So in that case, normally I'll put it as 1 out here. So this block 1 gets connected to block 2 for normal operation. Okay, but if I have to, if I give a 0 out here, then I'll be forcing a 0 into the block 2. So this CP and OP output should be available at the IO pits, on the IO pads and on the pins of the chip, right? So if I give a signal 0 out here, then I can observe the output of the block 2 out here, right? And now with a signal 0, I am forcing a 0 input into the block. Okay, is this okay with all of you till here? Okay, so these are the two additional kind of gates which you can insert in between the blocks and take these CP and OP outputs to do some limited testing of these block 2 and also to verify the output of block 1. Okay, is it okay? Okay. Yeah, we are going to use an mux. I am going to discuss that. Okay. Now, if you see here, here what we have done is this is an 1 and this is this is an OR gate and this is an AND gate, right? So normally I give CP 0 and CP 1 as 0 and CP 2 as 1. In that case, for normal operation, this gets connected like this, right? Now if I give CP 2 as 0, so this is an AND gate, so I will be able to force this to 0 for testing, right? And similarly, if I have to bring a 1 out here, right, I give CP2 1 and CP1 1 here. So I get a 1 from here, 1. So I can force this block 2 to 1. So if you see here, by having one AND gate and an OR gate and two control signals, so I can force either this block 2 to 0 or block 2 to 1, or I can have, right, in a normal operation, I can connect the block 1 to block 2. So I have now two input signals which can do this 3 functions. Okay, So like Raghavendra I think brought out, you could also use an mux also out here, or I think Saubhagya brought it. Okay, you can use an mux also here. Okay, now when you are using a mux, okay, this is the one with CP2 controls the mux. Okay, it will either select block 1 to block 2, or it selects CP1 input to the block 2. Now the CP1 is available and on the as an input and a pin. So you can give 0 or 1, okay, to force this block and input 0 or a input 1 in, okay, 0 input or a 1 input you can provide to this block 2 using this input pin CP1 and using this control signal CP2 through a mux, routing the CP1 signal into the block 2. For normal operation, you can again give a 0 at CP2 and connect block 1 to block 2. Okay, so this is another method of doing this. Okay, so now if you see here, now you can have various, like from each of these blocks you could have various, this is taking from block 1, so there could be hundreds such blocks, right? So we can't afford to bring output lines from each of the blocks, okay, from each of these blocks, okay, to the output pins. Okay, so if you, then your chip size will increase, right? You can't do that. So generally the number of pins which is available will be limited, right? You can't have just for testing purpose, you can't earmark a large number of pins. So what we can do is we can use within inside a mux, okay, and have few control lines which will select which which test point is to be routed towards the output. So within the chip you can have like these several test points, okay, for observability, right? So all those lines will be brought into one mux, and you can use some control signals, right? So now obviously you can see that instead of having an n number of pins, you can just have log n, right? So so if you have x control lines, n control lines, 2 to the power of n output points can be routed out, right? So you can use a mux out here. Okay, so the advantage is there. Okay, obviously disadvantage is that only disadvantage, one major disadvantage is at any given point you will be able to see only one output, right? So you have to visualize, okay, you take 111 output, okay, and then you need to visualize what could have gone wrong. Okay, so because if you have multiple outputs at a given time, it will be easy for debugging a fault, but then that requires more hardware and more number of pins. So this has got a disadvantage that you have to know the design properly to fix a fault out here, because you are taking only one particular output at any given time. Okay, so you can use these kind of circuits also, where you have an mux to minimize the number of test outputs, okay, so pins on a chip. So you can do that. Similarly, input okay, so here also now you are using n pins, right? So instead of that, you could just put a counter out here also, and during testing you can activate this counter. So this counter is also within the chip, within the chip, right? So as the counter keeps moving, okay, this mux will keep getting switched, right? So you just have to give one control line now here to activate the counter. Okay, now so you will have to wait for this counter to run, and you can get the entire outputs. Okay, so this further reduces the requirement of input pins, right, to control. Okay, now again every circuit, every concept will have its own pros and cons. Here the disadvantage out here will be, okay, you can see that, okay, you have to if you have to reset this counter, okay, or you have to program this counter to a specific value, all those things may not be possible equally easily possible, right? You might have to run the counter for the entire duration, okay, and get the full cycle output to analyze the fault, okay. So this is some, but the advantages is far much greater, that you don't require at all, you just require one particular pin which requires to activate this counter for testing, okay. So there should be some provision for resetting it to 0, okay. Once this signal goes high, it has to start from 0 0 and go to the maximum. So that counter functioning can be taken care of within the chip, that design can be taken within that chip, okay. So you will get all the outputs available here, which you can take it into a log file and then try to find out and debug if there is a problem, okay. So this is one method of doing it. Similarly, we can have for the input side also, okay. So you could have an counter out here, right, which is running, and then you have a single test input out here, and you have an demultiplexer. So based on the counter point, this input will be routed to which so like this output is going to this block, this can go to the next block. So this is again routing the input test vector to different blocks using a demultiplexer and an counter, okay. So these are all known as ad-hoc testing, okay. So you find here, is it understood? You have a single input line, you have an counter. So based on the counter, this demultiplexer will route this input signal to one of the blocks which is being tested, okay. So this has to run in sync with the counter at the other side, and then you can route these test signals into one of the blocks, and again you have this circuit at the output, so you can get the desired output. So these kind of things also can be done for testing. Okay, before moving further, let us try and understand what an static glitch is, because I want to drive one more point about testability. So before that, I need to explain you what a glitch is, and then I will move on to the testing aspect, okay. So if you see here, this is a circuit out here, okay. I have the function is AB plus B dash C, okay. AB, this is going to give me AB, and this is B dash C, okay. So this is now suppose these are the these two vertical lines, okay. The gap between these two vertical lines indicate one gate delay, okay. So we are assuming out here, this is just a simple example just to illustrate one point what a glitch is. We are assuming that the inverter has got this much delay, and gate, OR gate, they all have equal gate delays, so this is just a simplified waveform, and this may not be the actual case, but just to understand the concept. Now these vertical lines are the delays corresponding to one gate delay, okay, irrespective of what gate it is out here. Now if you see here, initially A is permanently 1 and C is permanently 1. B is making a transition from 1 to 0. After one gate delay, inverter will make a transition from 0 to 1 out here, right. And this AND gate also, after one gate delay, it will make a transition from 1 to 0 out here, right. So now from here, if you see at this particular instance, you will find here for this OR gate, okay, there was a 0 out here earlier, and 2 was 0 here, and now this has gone to 0. So this will make a transition to, the output will make a transition to 0, because this has become 0 out here, and this is also 0 here. So this will make a 0 transition, and this output, okay, out here, okay, and 2 will make again a transition 1, because now B has become 0 here. So I have 1 1 here, this is going to make a 1, so this is going to make a 1. Now at this instance, both the inputs to this, now one input to this input OR gate is 1, and then it will make a transition to 1. Now if you see here, the initially I had, okay, 1 1 1, right. In that condition also it is supposed to be 1. For 1 0 1 also, I am supposed to have 1 as per this function, but it's making a transition to 0. So this is known as glitch out here. Okay, now why has that glitch come in? Because see, if this has become 0, so this gets reflected here after one gate delay, so this becomes 0, so the output, whereas now one is supposed to come from here also, because this 0 needs to get becomes 1 out here. Now 1 will come here, but in this path there are 2 gate delays. So from here there is only 1 gate delay, and here there is 2 gate delays. So in between you have the output going to a low value. Okay, so this is known as glitch. Okay, so these kind of circuits and we have to take care to avoid these kind of glitches in the circuit. So what do we do? So what is the cause of this glitch? How to identify where all they would be probable glitches and how to avoid that? So if you see, when we make an K map out here, this we might have studied in our BTech classes. Now how is this function? The same function, you have 1 1 out here, 1 1 here. This is the K map, right? So these two min terms will be clubbed together. I get an A plus B, and this is B bar plus C, right? So this is how this is implemented out here from this K map, this function, if you see here. Okay, so why this glitch has come? Because you have left these two adjacent ones. Okay, you have not put a box over here, and that is the reason why that glitch has come. You have 2 independent boxes out here, 2 adjacent ones, and there is a 0 out here. Okay, so sorry, this is a 1 PC. So these 2 ones have been left alone, although they have been covered by individual blocks. 2 adjacent blocks have been not linked together. Okay, so, and that is the reason for an glitch. Now to avoid that kind of glitches, I can put one more additional box out here, right? Now this function gets modified as AB plus B dash C plus AC, right? This implementation gets modified, but again the function remains same, because there is an in the midterms there are 4 out here, there are also 4 here. So the final output remains the same. Only thing is, by making one more box out here, right? 2 adjacent ones are being covered here, right? So this is like putting an additional gate. Now the circuit gets modified like this. You have an additional gate which is coming out here, right? Now if you see here, when one is making a transition to 0 out here, right? So this is going 0 here, but you have inserted one more AND out here. This is AC, both are 1 here, so there will be 1 here, so there will not be any output glitch. Okay, like it going to 0 and coming back to 1, so that situation will not happen. So you have included this also implements the same function out here, like the output will be the same. If you see, for all the 8 different input combinations, okay, you will have the same output out here. Only thing is, a glitch will be avoided out here. Okay, and the glitch has been avoided by putting an additional AND gate out here, right? By these by putting this so additional hardware is required, but it is an glitch free circuit. Okay, so now when you are handling glitch free circuits, so you have to be very careful with your test vectors. Okay, so suppose if this line is stuck, you have to identify whether this line is stuck at 0 out here, right? So you will not be able to do that at all, because you will find that how to give this particular, how to check whether this is stuck at 0 fault. You might have to give an test vector of 1 1, right? You have A and B and as 1 out here, but you might find there is an alternate path available. Okay, so still this output will always be a 1. So you may not be able to for such circuits, you may not be able to identify make an for these kind of redundant where there are redundant elements, you may not be able to get a test vector which will which you can use to fix whether there is an stuck at fault in a particular path. Okay, so you will keep wasting time trying to find out what is the test vector in those cases. So whenever some hazard free circuits have been made where there are some additional paths have been put in the circuit by the circuit designer to avoid hazards, the test engineer has to know that and there are redundant paths available. Okay, if there are redundant paths, then you should not waste time trying to fix that fault. In that case, you have to just target the output function whether you are getting or not. Okay, at each node, if you try to make test vectors, then it will be waste of time. You know, we will not be able to create a test vector at all to fix that and to identify that fault, because there will be some alternate path will always be available. Okay, in those cases. So that is what. So the test engineer has to work in conjunction with the circuit designer, and the circuit test engineer needs to be told that in a particular circuit to avoid glitch, there have been redundant circuits have been provided. Okay, so that he has to take care of that aspect also. Now this was all Ad-hoc scan. If I go back here, I told there were two methodologies. This was Ad-hoc design. Okay, now here if we go to these things, method of test points, multiplexing, deep multiplexing of test points, time sharing of IO, we saw these things, partitioning of registers of large combinational circuits. So these aspects we have discussed. Now we are going to talk about scan path design. Okay, now what is scan path? Okay, now you have an combinational, generally you have pipelined structures, right? You have a combinational set of combinational circuits, then you will have flip-flops, then you have again another set of flip-flops, then you have another combinational circuit. That's how most of the circuits are designed, right? So what we do is in scan design, okay, so in each of these flip-flops, right, you give some test vector initially, right? So the output you give and you just give one clock. Okay, so the output of all the combinational circuits will be captured in these flip-flops. You give one test vector, one clock, so all the output of the combinational circuits will be available in these flip-flops. Okay, so you have this option of into the flip-flop you can here you can put in mux. Okay, normally for normal operation the output of the combinational circuit will come to the flip-flops, and then when you are doing an scan, the output of the flip-flop will be given to the next flip-flop, and this output of this flip-flop will be given to the next flip-flop. So you see this is this flip-flop, so all again the output of this is flipped here. So once you give one set of test vectors, you give one clock, you capture all the outputs of all the combinational blocks in the various flip-flops, and then you try to get the output. Okay, how can you do? By doing a serial shift operation, right? So serially you keep moving the data from one flip-flop to other and you get the output. Okay, and how to give the test vector for each combinational block, that also see this is a combinational block, this is a combinational block. So initially while I am doing testing, I can put it into the test mode and put the test vectors into each of these flip-flops, right? And then when I give a clock, so the input which I have given here, that becomes the test vector for this particular block. Okay, and then once I give the clock, these flip-flops will now hold the output of the previous stage. Okay, before the clock, and I can put in the test vector into these flip-flops. So these flip-flops can be serially in, you can pump in that required test vectors, and serially out you can get the results of the various combinational logics. Okay, is this concept understood by all of you? Yeah, Vinay, is it okay? Saubhagya, what we are doing in scan test. Okay, so this is how a scan test is done. Okay, now these are some way of implementing the scan flip-flops, okay, for the testability. Right. So you can use an multiplexer out here. Okay, so scan means the serial input will go to the flip-flop, and scan equal to 0 means the data will go into the flip-flop. Okay, the same thing can be, this is shown out here in the transistor level out here. So this is just a pass transistor mux, if you see here. Okay, so that is done out here. So this circuit, or you could instead you have an input and an output. Okay, these clocks itself can be modulated based on the scan signal. Okay, so if for a scan is equal to 0, it will give one phase of clock, and for scan is equal to 1, it will give the other phase. So you can use these kind of circuits also. So you can analyze these circuits. These are the various ways of implementing it. Okay, implementing this particular scan and the flip flop. So these are the circuits which you can try and these are all master slave flip flops, right? So where is the second approach used? What is the second approach you are talking about? Phases, is it? Okay, no, if you see here, it is a different way of implementing this. Okay, it works the same thing, right? If the scan signal goes high in this, probably these gates should have been XOR gates actually. Okay, it's shown as an OR gates. So if you see the scan signal is 0, okay, the phase will be available here, and phase it's 1 out here, this will get inverted out here. If the scan signal is 0, then the phase will get as it is, it will come through. If scan signal is 1, this will get inverted. Okay, so these two signals will be out of phase always, right? So if it is out of phase always, if scan is equal to 0, if you see, these are the transmission gates which have been used, right? And if you see here, for this NMOS, I have given an phase bar signal, and here it is given an phase D signal. So they will get swapped. One of them will get connected depending on the scan signal. So this is one particular way of implementing these flip flops out here. Okay, so now you could have something known as built-in test also. Okay, so what it does is it generates an pseudo random signals within the chip, and it is given to the logic circuit. Okay, and then the outputs from various stages. So once you give a pseudo random signal, it is not one particular test signal, but you are giving, say, the pseudo random signal generates an say 100 signals. Okay, so all the 100 signals are given, and the output is captured, and all the 100 outputs, each one of them is not analyzed whether it is correct or not. Okay, the outputs is combined into a syndrome, and we finally check whether the syndrome is correct or not. Okay, so this will be clear in the next few slides. Okay, basically in a built-in test, you generate some random test signals, you give it to the circuit, and you take the output. Okay, and each output is individually not checked. Okay, because then you will have to have an lookup table for each of the input tables and keep verifying whether it is correct or not. Rather than that, what is done is built-in test. You give a set of, say, 100 test vectors. You take the 100 outputs, you combine them, and you after that particular combination, whether the net result you check with your whatever whether you are getting the desired result as per your design. Okay, so that is known as built-in test. Okay, now this is how it is done. Okay, you have an test generator. So normally inputs will go to the circuits, and outputs will be available. Whenever you are doing a test, built-in test, there will be a test generator which will generate a test signals. Okay, test vectors, a set of test vectors that goes into the test. The results will be processed here. Okay, and then after the entire test signal gets over, the response is, we'll see the response if it is as per the desired one. If it is not, then I pop up out error. Okay, I tell, okay, there is an error which has been encountered. Okay, so this is what a built-in test does. Okay, now the advantages of this is on a lower cost because of external tester is not required. Okay. So what is done in a built-in test is I have a control signal. Okay, there is a mux out here. So whenever the control signal for test is given, the test generator generates a set of test vectors. Okay, so that test vector is given to the circuit. Okay, so this is continuously various test signals will be generated here, and the output is now monitored. Okay, it is not that each output will be monitored and then you produce an error output, because that for that you will require a large memory and hardware. So all the outputs will be combined, okay, and then we will see, that is known as a syndrome, and then we finally verify that whether that syndrome is correct or not. Okay, so I'll explain you that in the next few slides. Okay, and then the final error is given at the output. Okay, okay, Bera, if you are not clear, after next few slides you can ask me again. Okay, so the advantages of a built-in test is like, these are all issues which you can see. Lower cost due to external tester is not there, in system, so high quality testing can be done, faster fault detection because you don't have to again put external measurement tools and all. Inbuilt it will just run the test run, and it will give overcome spin limitations, reduces maintenance and repair cost. Okay, the issues is test strategy, whether it has to be the test vector generation, whether it has to be random, exhaustive, or certain specific deterministic, that you need to design. The test engineer needs to design. Okay, circuit partitioning, test pattern generation, counters will be required. Okay, linear feedback shift registers will be required. We'll see what it is. Okay, ROMs will be required, because ROMs will be required. That means when you are generating the test vectors, okay, you say you give some 50 test vectors and you get an syndrome, you verify it with what you are supposed to get, right? Then you run another set of 50 odd tests, and then you verify. So there will be an right. So there will be a requirement of ROM also, right? A response needs to be analyzed. Okay, so it is test control and scheduling. So this response is to be analyzed means we'll see that when we get the response, we'll have to seeing the response, we should be able to say a set of response, we should be able to say whether what is the fault in the circuit. Okay, so that diagnostic also needs to be done. So now if you see here how to generate the test vectors, okay, random. So this is known as a linear feedback shift register or pseudo random generators. If you see here, there are 3 registers. Suppose I have preloaded 100 in these registers. Okay, and then I have taken the output from here, put an XOR here. I have taken an output from here and XOR here, and this is an shift register. Okay, it's moving out here. So now 100, right? Now here what happens in the next cycle? If you find here, this is an XOR gate, right? So you will find this output is coming. So you will find here by using these kind of circuits, you can generate some random signals out here. Right, so that is how these are known as pseudo random generators. So this is just one example out here where I have used only 3 registers. You could have multiple registers, and you could have multiple XOR gates placed at different places. Okay, if you do that, various kinds of patterns can be generated. Okay, so these kind of circuits are also used for in cipher circuits, right, in for encoding data. Okay, so if you see here, so this is an pseudo random generating series. Okay, the pseudo random means it is random in nature. Okay, but it repeats after certain time, right? So if you see here 100 011 101, again after 100 it has come back here. It will again follow this sequence out here once again. So it is not entirely random in nature. Okay, so entirely random, means there is no correlation between the previous and this, but this pattern will again be repeated again. Okay, now here it is going to repeat after these many cycles again 100. We have encountered the first stage, right? So it depends on the number of registers which you have used and the number of XOR gates which you have used. Okay, the way you have connected, so that will determine how big your pattern is, how at what frequency it is repeating this sequence. Okay, it could repeat after every 4 cycles, or it could repeat after every 30 cycles. Okay, it can depend on the number of registers which you have used and the number of XOR gates and the way they have been interconnected. Okay, so that will determine. So you can generate these kind of random test signals. Okay, they are not random 100% random, it's known as pseudo random because there is a repetitive in nature. Okay, and they follow a particular sequence also. Okay, it is not that every time 100 the next state will be this. Okay, only thing is they are random in nature, means they are not sequential. Okay, randomly these numbers they don't have an correlation with the previous data which is available. Okay, so these are the kind of circuits which are used to generate the logic circuits. Okay, once these this is like a single bit signature register. Okay, now if you see here, this is the test input which is available. Okay, now this is the test vector which I am giving here. This is the output which is available here. I am delaying it out here. Okay, I have used one here, and I am using an XOR gate. Okay, what this does is if it is 0 first input, another 0. Okay, and in the next cycle also 0 0 will give 0, so the counter will not move ahead, right? Whenever there is a change, okay, from 0 to 1 or 1 to 0, the XOR gate will trigger one signal and the counter will move. So if I run 100 test vectors, okay, the counter might read, okay, say 5, 10 or 50 depending on the output signal, right? So if I know beforehand that if I run this particular set of test vectors, my counter has to read 50, right? So that is how I will this is known as capturing the signature, right? So I don't have to verify that in each of these 50 or 100 test vectors whether my output was correct or wrong. What I do is I put this kind of circuit out here. I give 100 test vectors. I have put one circuit out here, and I just after that 100 test, okay, vectors, I just see what is the counter reading, right? Obviously, this I am not saying that this will be 100% foolproof, okay, because there could be multiple faults which can happen. So, okay, we again here also the concept is we are assuming that there would be not many faults, there will be only one odd fault. Okay, so in that case the counter, whatever is the counter reading, okay, so instead of monitoring each and every output, okay, a set of outputs, I run a set of test vectors and I put that into this kind of circuits, and I put a counter out here, and the output of the counter I will monitor after that 50 or 100 test vectors, and I will verify whether that counter is now reading the desired. So prior itself I have to know for these test vectors this will be the kind of outputs which is expected, and this counter has, so this you might have to refer to a inside a ROM to verify whether this counter is reading correct or not. Okay, so for each set of test vectors, if there is a problem there, then probably you can run one more test vectors which is in more in detail. Okay, so that kind of a hierarchical testing you could do. Okay, now this here I just showed single bit register. So if you have multiple outputs, okay, coming, okay, this is only single output coming, right? If you have multiple outputs, you could have some circuit like this, right? And then you could run a test vector, test responses are available here, and then you will see what is the final output. So depending on, you could run say 100 runs test signals, right? And depending on that, and the outputs, the value of these registers, they will keep changing. And at the end of the 100 test runs or 50 test runs, you can say what would be the value in these registers. Okay, if that pattern is known, you can just verify the end result instead of testing each result. So this is known as multi-input signature register. Okay, so this is known as capturing the signature after doing multiple runs. And in case there is a problem out here, then you can again you can do a detailed testing after that. Okay, then you could run smaller test runs. Okay, so that kind of logic needs to be developed. So this is known as built-in test logic circuits. Okay, is it like an CRC? Yeah, it is something like an CRC procedure. Yeah, it is something like that. Okay. Now you have an something known as BILBO also, built-in logic block observer. It actually combines the scan and the pseudo random generators and signature analysis. Okay, so this was one pseudo generator analysis which we saw here. Then that is known as we studied under built, and before that we saw the scan also. So this combines both these concepts. Okay, this is known as BILBO. Now if you see here, this is the circuit, these are the flip flops. These inputs D are coming from the combinational circuits out here, right? And you have these two control lines. So if it is 0 0, this circuit will work in the scan mode. 1 1, it will work in the normal mode. 1 0, it is going to reset all the flip flops, and 0 1, it is going to work in the test mode. So what I have done is I have just put these things in separate slides to make things clear. Now if you see 1 1, okay, the last case 1 1, you will find these AND gates are enabled here. One input is coming from C0. Similarly, C1, all these AND gates will be disabled because you have an bubble out here, right? So these AND gates will be disabled. The which is looking from top to bottom, the vertical AND gates will be enabled. Now the data from the combinational logic, and since it is 0 here, the XOR gates becomes transparent, right? So this data is available to these flip flops. It will work in the normal mode, right? Now suppose it is 1 0, here it is 1 0 is a reset. Okay, 1 0, if you see here, all the top AND gates will be 0, and the bottom AND gates also will be 0 out here. So you will have 0 0. So what with the clock going high, all the flip flops, the data will become 0. Okay, so that is to reset this flip flops to 0. You can do that, or you can give 0 1. What happens when you give 0 1? Okay, now if you see here, 0 1 is for the test. Okay, so the top signals will be activated out here, right? And then also you can give the top signals will be AND gates will be activated. So the data which is available, the test data which you require to feed it into these flip flops. Okay, first you can push in this data into these flip flops through serial input, right? And through the serial input port, and then you can use the 0 win output to do the normal test. Okay, similarly you can give an output of 0 0 out here. Okay, in the 0 0, what happens is all these top AND gates will be disabled, and the bottom scan one is here. What you are doing is you are enabling this also. So serial input after the test, serial input, you can give the serial input and you can move it towards the output. Okay, this is known as a scan. Sorry, the test vectors can be given out here, right? And here if you see here, if you give 0 0 here, this feedback loop can be established. So by giving these various control signals of 1 1, 0 1, 0 1 and 0 0, various kinds of testing methodology and normal working and resetting of the flip flops can be achieved. Okay, so this is known as BILBO method of testing. Okay, so with that we will stop for today. In case there is any doubts, you can ask me now.